Hello. Today I'm going to talk about software architecture challenges in process automation, from code generation to cloud-native service orchestration. So ABB is active in different business areas, among them electrification, motion, process automation, and robotics. Today I'm going to focus on process automation, where ABB delivers large distributed control systems which run big production plants, for example, for power generation, for chemical, for refinements, for paper production, and so on. And in this area we see a lot of software engineering challenges, trends from the IT world that are also relevant in the automation technology world. One is cloud-native infrastructures, so we are utilizing virtualized infrastructures and infrastructure as code technologies to orchestrate our distributed control systems. Currently we're converting our Windows-based applications into microservices and even want to extend that for control applications. Because the engineering and the configuration of our systems is very sophisticated, we're also looking at model-driven development to speed up the configuration of our systems, to aid data analytics and have even non-experts and non-programmers to make sense of data. We're also looking into low-code development. Then we want to speed up how we deliver features to our customers, and therefore we are looking into continuous integration and deployment. And finally, a big issue is also in cybersecurity, because the distributed control systems run on critical infrastructure in many cases. So they need industrial strength security according to a number of industry standards. Today I'm going to focus on 3 of those topics, which are highlighted here in red. Let's start with the model-driven development. So model-driven development, and I give an example on rule-based code generation. So if you consider a large process automation plant like this one here, which has a lot of equipment inside and lots of automation with actuators and sensors, these kind of facilities need to be planned. And often they are planned by chemical engineers, which have a good overview on how a production process works. And what they do is they use computer-aided design tools to come up with a construction drawing, which might look like this here. And this is a typical piping and instrumentation diagram. So it shows a number of the pipes in the plant, and then also the instrumentation in the sense of the controllers, the sensors and the actuators that are in such a plant. And in this diagram we see, for example, a tank or kind of a reactor where some substances are mixed, and we see some heat exchangers to heat up or cool some fluids. And then all these little circles in the picture are actually sensors. And there are also actuators visualized, like valves, for example. Now, all these different elements, they also serve as input for the automation engineers who program the automation systems. And what we do today is we take these P&I diagrams, and for a plant, there's not only a single drawing. Of course, there might be hundreds of P&I diagrams for a single plant, so it's a huge complexity there, which might be looking like this in a very much simplified fashion. And then many times our automation engineers have PDF files of that available, or even only printouts from the chemical engineers. And then they use that as templates to design the control logic and program the control systems. And for example, they are using languages like this IC 61131 language here, which looks a little bit like C code or Pascal code. It's actually industrially standardized. So this still involves a lot of manual work, and we want to automate that to a certain extent. So in the future, we want to turn these P&I diagrams from drawings into actual object-oriented models. And for that, we want to utilize standards. There's a new standard called DEXPI, which stands for Data Exchange in the Process Industries. And they have provided, this is a working group from the chemical companies around the world, and they have come up with a specification for P&I diagrams, for smart P&I diagrams, which actually specifies object-oriented concepts for all these different elements here in such a drawing. And if we have those object-oriented models, where we not only have circles and lines and arrows, but actually we have tanks and motors and valves and so on, then we can design algorithms around that and actually partially generate some of the control logic. For that, we want to employ a rule engine. And the rule engine shall execute rules which occur a lot of times in different plants, and they always end up in very similar code. And with this rule engine, we aim to generate the code automatically. There's a lot of related work for this topic already. So in academia, this topic has been researched for more than 15 years. And many of the existing works also base their control logic generation on P&I diagrams. They use different notations and different mechanisms on how they carry out the model transformations. Some translate into intermediate UML diagrams and then augment or extend the UML diagrams. Others use graph databases, and others use domain-specific languages. But most of them end up with a variant of this IEC 61131 programming languages and generate code from these diagrams in some sense. Just a very simple example to explain the entire idea of the code generation. Let's say we have here a very simple excerpt of a P&I diagram where we have a vessel, then we have here a pump, we have a valve and two feeding valves to this vessel. We have a level sensor, LS level sensor, and then we have a temperature controller here. Now, an automation engineer has a rule in his head saying like, if a vessel has a level sensor attached, so for example, here we have a vessel, it has a level sensor attached, and there's a level sensor high alarm signal. So if this sensor signals, okay, the level in the tank is too high and the tank is about to overflow, then close all the valves on pipes feeding the vessel. So this is kind of a safety function. We call it an interlock, which interlocks the level sensor readings with the valves that are feeding the tank. And this kicks in if something malfunctions, if there's too high level, and then these tanks are closed. So the automation engineers recognize this kind of topology in the diagram, and then they write the control logic for that. So here we have two situations. So first is the level sensor is connected to this valve 102, and then it's also connected to this valve 104. Then we can generate, or then we can create 61131 structured text from that. Here's a very simple notation. So we say here, if this B101 sensor has a high limit property, which is true, then we send the signal to 102 to open, and the open signal, we set that to false to close the valve actually. And the same we do also for this valve 104. So all the feeding valves are closed, and so the tank can drain and does not overflow. And this is a very simple situation, but actually in practice there are many more situations. In our case study, we derived more than 80 different rules, which are common across different plants and which can be reapplied to many different situations in such topologies. But the principle is always the same. For our approach, which we call Cayenne, we also develop a shorthand notation so that this natural language specification is a bit more streamlined and easier to express. So we say vessel alarm level high, and then we express the navigation through the topology just through this notation here, vessel pipe valve. And then we can say valve close, and then from this notation, an algorithm, a rule engine can match this kind of situation and then generate the according code for that. For our approach, we used a topology model, which is a little bit reduced compared to an entire P&I diagram, but it contains elements like vessels, heat exchangers, flow heaters, different kinds of sensors for level, flow, pressure, and temperature. We have pipes, nozzles, and junctions. We have heaters, valves, motors, and pumps. And this covers already a good range of the elements that you find in a typical process production plant. So from this topology, which builds up an entire graph connecting the different elements to the pipes, we can then run our rule engine and do some graph traversals to actually apply the rules. For the rules, we also have defined a domain-specific language as seen in the former slide, and that we did through a grammar, and we generated a parser for that so that we could easily specify that. Then we developed some tooling, and you see here an example of a topology model overlaid with the topology model elements. You see here these are really object-oriented concepts like a level sensor, valve, pump, vessel, and so on. So are not drawing elements like a circle or a rectangle. And they also carry a lot of properties like the alarm limits or the different coordinates. Then we also have our rule engine, and it has a very simple user interface where you can select different rule sets based on the domain you are in. And so if you're defining the automation for a paper mill, then it's different than from a mining production facility. And then you have a rule list and can select also different rules, can edit the rules if you have something specific for the plant. And then we can generate the control logic from those imported topology models. And then the tool gives you a lot of logging information to show you how the graph traversal works and what kind of code constructs have been recognized The code that is generated is then afterwards, of course, always reviewed by the automation engineers to make sure that it complies to the intended notation. Yeah, we executed 4 post-mortem real-world case studies to analyze how far can we get with this code generation. So we had inputs from an oil platform, a chemical plant, another chemical plant, and then a crude oil separator. These were plants that had between 400 and 7,000 I/O points. We had a number of P&IDs available, so these piping and instrumentation diagrams, 8 for one of the plants, but then up to 134 for another plant. We didn't analyze all of these P&IDs because not all of them were relevant for the control logic engineering, but for each plant we analyzed on average 10 different P&I diagrams and to derive the rules that we needed for the code generation. For our experiments, we used the manually engineered control logic coming from cause and effect matrices that the automation engineers had created when actually manually engineering those plants. And we used those as ground truths to compare our generated code against. We analyzed roughly 100 interlocks per plant. So interlocks are these situations where 2 elements in the topology are interconnected and need to be found to be working together. And then we generated the control logic for those interlocks for that. So we had different numbers of rules for that. In total, we have had about 80 different rules we generated from those case studies and then executed them. And you see here the process we did. So we actually worked with printouts and PDF files of the P&I diagrams to derive the rules. This is a one-time activity, and once you have the rules, you can apply them also to different plants. Here we see the photo of 24 different P&I diagrams, which we analyzed for one of the plants, where we also try to recognize the different dependencies in a plant between different elements to come up with the rules. Yeah, and then the results were quite encouraging. For the percentage of interlocks that we could generate from those diagrams, we aimed at a target of 80%, but actually for those plants that we analyzed, we were able to generate more than 90% of the interlocking logic. Many of those rules were also classified as generic, so they could be reused across different plants. And many of the rules also generated multiple interlocks because if you have those rules and they generate 10 or 20 different interlocks, then it's a big time saving, of course. In our cases, we didn't have many rules matching in multiple cases, but this can be explained because our cases were quite different. We had 2 different chemical plants, but those chemical plants were still very different from the oil production facility, and that's why some of the rules could not be transferred among the cases. This research is still not finished, so we will have a lot of open research questions. One is, for example, what is the most appropriate abstraction level for the topology models? We used a very simple topology model that was geared towards code generation, but there could be other ones, and the abstraction level is still an open question, especially if you also want to generate different kinds of control logic. Our second question, so far we've focused on interlocking logic, but there could be also sequential logic or regulative logic, which you could also generate. So this approach could be extended in that direction. And then actually those topology models could be also used for other things like generating process graphics to come up with user interfaces for the plant operators, or to feed simulation models, because if you have the interconnections and the topology of a plant, you could also generate a simulation model, which can then help in testing the control logic and testing the entire configuration that you have set up. So a lot of opportunities to continue this research. But this then subsumes our part on model-driven development, and the next one would be on continuous deployment. And here we're looking specifically on a plug-and-produce approach for field device commissioning, which allows you then to continuously also integrate new devices into such a process production plant. You have to imagine that a big production facility like this has many sensors and actuators, can be 1,000, can be 10,000 of different sensors. Each of these red dots is a sensor, like for example this flow meter here or this temperature transmitter. You can have different actuators, and they all have to be installed and configured, and this is quite a laborious process and costs a lot of money. So the installation procedure is called commissioning, and the commissioning consists of a number of steps. First, you have to, of course, place the sensor and, for example, screw it into some location. Then you have to connect it to power and also to the network. Afterwards, you have to set some field bus addresses, retrieve the sensor type that you are looking at through your laptop. Then you have to select a device package, download that device package, enter some configuration parameters to really configure the device in a specific context. You get the addresses and have to map them to the logic engineering, and then you map the program variables that you have in your logic engineering onto those field bus addresses. Finally, you can compile and download the control logic for that device, and then you have to repeat that for all the different devices. So this was only for one device, but if you have 1,000 devices, it's a lot of work. Afterwards, once you've done that for all devices, you can start the production and produce something, but from plugging to producing takes a lot of time. So it can be 60 to 90 minutes per device. And if you, of course, have 1,000 devices, then yeah, this is a very long activity. What we want to go for is that we only place and connect the sensor, and then some automatic steps happening, so that once yeah, the configuration has been automatically downloaded, that the production can immediately start. And our aim is to achieve that in less than 10 seconds per device. So let's have a short example, and to also explain the requirements for such an approach. We have here an industrial boiler where some fluids are heated. Then we have a laser level transmitter measuring the level in the tank. We have a controller that reads the sensor values and sends and signals to a pneumatic valve. And so this regulates the filling level in the tank, and could be a chemical reaction that happens here. For a plug-and-produce approach, we first need to automatically discover those devices newly connected to the network. We need to have standardized device descriptions, because if we want to connect devices from different vendors, then we cannot work with proprietary notations. We want to perform an automated signal matching between the controllers and the sensors. Then we have to have an approach that supports real-time communication. And finally, we also want to support device replacement. So if we have to replace a device because it's malfunctioning or because we have a newer version available, then the entire approach should support that. There have been also a lot of work in literature and in the industry, generic plug-and-play approaches from Microsoft, also the UPnP device architecture for more network devices, but these were not suited for industrial devices with special communication protocols. On the other hand, in the industrial domains, there have been also plug-and-produce approaches, mostly still tied to proprietary protocols, and they didn't support device replacements. And finally, a newer line of research looks at IoT devices, so Internet of Things devices, and has proposed reference architectures for that. And these can be used as a template also to design a plug-and-produce approach for distributed control systems. Still, those approaches used very simple information models because these IoT sensors are usually quite simple. For us, they are not suited for many of our resource-constrained devices, which have very limited computing capabilities. Yeah, we propose in our research an architecture called OpenPNP, so Open Plug and Produce. This means, and the open means that we are basing also our architecture on standards. It's not proprietary for ABB, but it can be also used by other automation vendors as well. First idea is to equip each of the devices with an OPCUA server. An OPC is a machine-to-machine communication protocol, which yeah, can express also the device configuration. And we add a software service, which is actually an OPCUA client, because it's a plug-and-produce software service. And this runs autonomously in the background as a daemon and recognizes newly connected devices and newly connected automation controllers and can bring them both together. This is our main contribution, the service, which can be plugged into different plants if we have all sensors equipped with OPCUA servers. OPCUA is yeah, the Open Platform Communication Unified Architecture, so it's a machine-to-machine communication protocol on top of TCP/IP. There's a binary version, binary protocol also available, but you can also communicate OPCUA via MQTT, for example, and the special capabilities for this protocol are that it has a very sophisticated information model. You can define very extensive and elaborative information models for your devices or your different controllers, and that's why we utilize that. So it's a client-server protocol, and here we see a server in this black frame, And the content of the server is an address space. The address space contains nodes which can be interconnected, and each node represents a static or dynamic value about some device in the plant, for example. This could be a temperature reading from a temperature sensor, and another device could be a configuration parameter, for example, the limits that a level sensor uses for measuring something. And those nodes are connected to real objects, so they read real readings, for example, and can be dynamically updated. And then OPC UA clients can connect to such a server, open a session, and then read out those nodes, the current values. And if you have a dynamically changing value, an OPC UA client can also set up a subscription to such a value. And then we have monitored items, and then the clients get notified all the time with new values for these items. So our reference architecture, which is based on OPC UA, looks like this in more detail. So we have the field device here. And the field device could be a sensor or an actuator. It now carries a device OPC UA server, which includes standardized information models like the OPC UA for devices model, the Namur NE 131 models, or IEC 61987 models, something like that, standardized information models. And it also carries an OPC UA local discovery service, and this allows the device to be automatically discovered in a network. A very similar thing we do for the controller, for all the controllers in the system. There could be dozens of controllers there. Each controller carries a controller OPC UA server, which has also representation of the control logic inside the OPC UA server. So the Plug&Produce service can use that later to configure the controller and set up the subscription to certain devices. It also carries an OPC UA local discovery servers. And as an information model, we use PLC Open, which is also standardized for control logic concepts. All of them are connected via Ethernet. And then we have on a server layer, we have our Plug&Produce service running on an operations server. This is actually an OPC UA client, so it connects to the devices, it connects to the controllers, and it can also connect to a device management system where it can download device drivers. And those drivers can also be downloaded to the device via OPC UA. And it can also retrieve engineering data from an engineering repository, which can contain pre-configurations of the devices that have been done before commissioning the plant. The device drivers can also be retrieved from a public driver repository. So we can have different ways of getting the drivers to the devices if that's needed. Good. With this architecture, we hope to cover the requirements. For the automated network discovery, we use these local discovery service from OPC UA. We rely on standardized device descriptions encoded in these OPC UA servers. We provide the automated signal matching via our Plug&Produce service. And then we also support real-time communication via Ethernet. Could be supported by techniques for time-sensitive networking to have really deterministic, reliable real-time communication here. And then we also have come up with a concept for device replacement. The device replacement workflow is depicted here. Without going into all the details, which you can also read up in the corresponding paper, it first notices from an operator what kind of device shall be replaced, and then it stores the existing device configuration and changes the neighboring devices into a simulation mode so that they do not interact with the process anymore. And then it signals to the commissioning engineer that it's now ready to disconnect the device. And afterwards, the new device is installed, and then it can again go through this Plug&Produce approach of automatically discovering it and uploading the formerly stored configuration, and then rematching the signals and connecting it to the controller. To validate the approach, we created a prototype based on hardware. So we had different communication boards for the Ethernet communication. We used a level sensor and the temperature sensors. We had equipped them with Ethernet connection and installed OPC UA servers on them. Here's a power supply also visible. And we used some Raspberry Pi devices to simulate controllers. So now we wanted to check how much can we speed up actually the commissioning. So the process of placing, connecting the sensors under the production start. And our aim was to get that down to 10 seconds. So we did a comparison between the classical approach and said, okay, we have like 9 different steps of the commissioning, which we see typically. And we also had estimations from domain experts how long these steps take. And then we compared that to our OpenPNP approach and measured also the times based on our prototype. To cut things short, you can read up the details in the paper. The configuration time in this scheme from step 4 until 6 to 9 reduced from 10 minutes in the manual approach to approximately 46 seconds in the automated approach. So not exactly the 10 seconds we were aiming for, but actually this is a very good reduction of more than 90% based on the automated transfer of the configuration parameters, the automated identification of the devices in the network, and the automated signal matching between the controllers and the devices. Of course, this is also supported by the faster Ethernet connection that we are using compared to the formerly analog connection. But all these factors combined, they sum up then to a 90% time reduction, and there's also a cost reduction. If you imagine a plant with 10,000 devices, this can accumulate to 1,500 working hours that you actually save. So these were good results. We also verified the real-time capabilities and the performance that you need for such an architecture by measuring CPU utilization in a simple scenario. So we had here 2 industrial controllers and a lot of field communication interfaces, and we set up 6,000 I/O points with 100 milliseconds update rate. So we had 60,000 signals per second. And then we had 2 controllers, which we simulated with Raspberry Pi devices. And then we also compared the OPCOA PubSub communication to the OPCOA client-server communication. With the PubSub, we reached up to 40,000 signals per second per controller. So we can, if we have 2 controllers, we can support 80,000 signals. So this scenario is valid. And with a client-server approach, and if you assume we have 30 clients in our system, then we can manage up to 10,000 signals. So if you only have 2 controllers, this would not be sufficient. However, the PubSub's communication in this case is beneficial, so it should be used for actually communicating the signals. In our cases, the CPU was the bottleneck, but in general, we saw good scalability even on small devices. This field of research also has some open questions. Still, we assume that the device configurations that you need are written manually, so that some engineers write those values into some engineering tools. But we thought maybe some of those values could be also generated if you know the models of adjacent devices that are in the neighborhood of a device. If all of them have kind of a digital twin representation, and you can get access to that through an OPCOA server, then perhaps you could also generate some of the configuration parameters and do not have to set them by hand. Then we're also working on lifting the plug-and-produce approach from individual devices onto entire plant segments, and looking into simulation again to test systems upfront. So if you have these sophisticated device models and also the configuration parameters, this gives us more possibilities for testing the systems and removing errors before actually commissioning the system. Finally, we're also looking at cloud-native infrastructures, clusters, running software containers for our server-side part of the control systems. And here the example is on an approach for Bumpless updates and live migrations of control applications. So the setting is like this. We have a plant operator who looks at who supervises a production plant. And often those plant operators want to do small changes because they want to improve the production, or they optimize something or work out some smaller errors, and they want to do that during production. However, if we do that during production, we have to shut down the plant and then patch the firmware of the controllers. So we need an approach to update the control logic without interrupting the production process. Because if we have to wait until we can interrupt the production process, then it can take weeks or even months. These cycles are not so frequent, so the changes that a plant operator can do can only be transferred very infrequently. So we want to do that during runtime and without interrupting the process. Again, a very simple example where we have a control application for an industrial boiler with the boiler here, with a feeding valve and an outflow valve. We have a level sensor measuring the filling level in the tank, and we have a real-time controller that computes some control algorithms here cyclically. So every 100 milliseconds a new value is calculated, and then the signals from those calculations are sent to these valves. And now the question is, how can we update this software here actually without shutting down the controller and patching the firmware? One thing you have to consider is that in the controller logic applications, they are stateful, of course. For example, if you consider here, we have a heat exchanger and a temperature transmitter, and then a temperature controller, which controls the actual temperature in the heat exchanger. Then the code for that temperature controller is displayed here on the right-hand side. So it's a typical control algorithm which has various inputs and outputs, and then it has some local variables. And then you have some algorithms here which do the regulative control. And these algorithms, they have internal state. So the next value is computed from some former values. So if we want to switch between an old version and a new version of a software to run an update, then we have to carry over the internal state from the original version to the new version, so that the new version is initialized with the same internal state as the original version. There has been also related work in this area. For embedded systems, there have been different approaches for dynamic software updates, but those approaches were restricted to individual devices and did not use a container deployment. So they did not allow an update of the container runtime or the underlying operating system, but only supported smaller changes to the control applications. However, there have been also tests with running control applications inside software containers, like Docker containers, measuring the jitter on a real-time operating system, and they demonstrated that in principle you can also run PLC control logic for process automation in those containers with acceptable jitter. So this is a prerequisite for what comes then next in our approach. And finally, there are also some state replication approaches for container orchestration engines. Several authors have looked into Kubernetes systems and providing approaches to do state transfer for stateful containers. However, those approaches did not use signal control applications and had comparably simple internal states compared to what we use here. So our idea was then to take the situation and do the following. We say we exchange this real-time controller with a Kubernetes cluster, and in this Kubernetes cluster we run the original PLC application in a Docker container, and then we have an updated version of the control application which runs actually in parallel. If you start this updated version up, it's initialized with default values. So what we have to do is transfer this internal state from the original PLC to the updated PLC. And this state transfer we do with OPCOA again, because those controllers, they have those control algorithms, control execution engines have already an OPCOA server integrated. Now the challenge here is that the state transfer has to be really fast. If we have a control application that computes a signal every 100 milliseconds, and the control algorithms take like 10 milliseconds to execute, we have an idle time of approximately 90 milliseconds, where the control application is idle and can, so other things can execute. And ideally, our state transfer shall happen in this idle time, so below 90 milliseconds, so that not a single control signal is actually lost. So that's the challenge where we want to aim for. Some background on Kubernetes. Kubernetes is an orchestration framework for large computing clusters. You have a control plane with a master node, and then you have a couple of worker nodes in an application plane. Each node has multiple pods, so up to dozens or hundreds of pods, and a pod can contain one container or even multiple containers, which are scheduled by the kube scheduler to run on an appropriate node. The Kubernetes system stores its entire configuration and deployment schemes in a database called etcd, and users can interact it with this database via an API server, and can then change the deployment in the cluster or instruct the Kubernetes scheduler to launch, for example, new replicas of a component. Kubernetes also includes a standardized extension mechanisms via operators. You can implement your custom Kubernetes operator, which then interacts with the API server, the database, and the kube scheduler to do some custom scheduling of containers and resources. And this is what we also reuse in our approach. Our architecture looks like this. So we have a typical Kubernetes system with a master, and we show here only 2 worker nodes, but in a real scenario, we would have probably dozens of worker nodes. And in the same simplified fashion, we show only one control application. The control application is the 6.11.31.3 control application running in an appropriate execution engine. and it also carries an internal state. We have put the engine into a Docker container and then run it as a Kubernetes pod. And the Kubernetes pod exposes OPC-UA interfaces for signal inputs, but also then to feed this engine with new OPC-UA configurations. For example, if you want to update the control applications during runtime. If we have an update either to the deployment or we want to change something in the container version, or we get a new program uploaded via an engineering tool from an automation engineer, then our virtual PLC operator detects those changes and starts the following procedure. It starts a second instance of the PLC program, which actually carries then the updated program, but it's still initialized with the default internal state. And we run this on a second worker node, for example. And then afterwards, it also arbitrates the downloading the internal state from the original PLC program and uploading this state into the new program, and does this within a single control cycle. We also built a prototype for this system, and we use Kubernetes based on the StarlingX open source distribution that carries Kubernetes, Docker, and various other tools. And we used OpenPLC, PLC OpenLogic as a control execution engine here. The dynamic flow that the virtual PLC Kubernetes controller goes through is here. Once it detects an update request, it starts the second runtime as said already. Then it connects to both runtimes, and then actually in this red phase, the performance or the time critical path starts. It pauses both runtimes, then it extracts the internal state from the original runtime, and then sends it to the updated runtime, it deserializes and then extracts it, and then unpauses both PLC runtimes. And these steps from 4 to 9 have to happen in less than 90 milliseconds. Afterwards, we also have a phase to verify the correct behavior of the entire procedure, because we also allow a rollback of the updates if they are not correct. This is based on some thresholds that have been configured beforehand and can be done manually, or it can be done also by a procedure. And if the new updated version of the control logic gives wrong signal values or undesired signal values because there's some error in the update, then we can also roll back the update and stop the second runtime and inform the user. If it goes through, then we actually disable the runtime 1 from writing outputs to the control valves, for example, and enable the PLC runtime 2, so the updated PLC runtime, to write those updates. And then afterwards, the update is successfully carried out. Let's also run a short demo here. So we see here a Kubernetes dashboard, which shows you the different pods that have been deployed in Kubernetes and their CPU usage. And we have here deployed our OpenPLC pod, which carries the control logic, and also has a graphical user interface, this dashboard here, and we have a very simple example configured. Let's monitor what's happening actually in the process. So we have this fluid level in the tank that changes dynamically, and then we have configured an upper limit for this fluid level. So in our case, the upper limit shall be 600 centimeters, for example. So that's the desired filling level of the tank. And if you configure that, then the control algorithms kick in, and then they change the fluid level in the tank actually changes, because now the flow transmitter that feeds the tank actually is opened, and then the fluid level rises in the tank. But once it reaches this desired level of 600, then the input valve is closed and the output valve is true, and then the control algorithm changes all the time the opening and closing, and keeps the level. Now we simulate an update through an engineering tool. Here we use a function block language and insert a new function block into the control logic, connect the blocks again, and then we recompile the code. This is not time critical now. This can be done offline without interrupting the process. But once we have that, we can then also run the updated code in parallel to the original code. So we have now here an updated pod that is running, and we see also the second user interface for that updated pod. However, as you see, the fluid level is still the the existing one, and still on a default value, and the level to maintain is still 0 because it does not carry the internal state of the original one. Now we run our operator, and very fastly it transfers the state over to the novel instance of the control application. So now in our case we can monitor then if the behavior of the process is valid, and afterwards we can then reconfigure the system to let the novel version write the outputs, and then we can stop the original version of the PLC runtime and, for example, archive that. So that concludes our demo here. This was just a proof of concept here, but we also carried out then a larger case study with a liquid natural gas plant with 18 controllers. So this plant is in Norway, and yeah, we derived some experimental data from those controllers. So we found that those controllers use control applications with up to 100,000 internal state variables per controllers. So we use that threshold as for configuring our experiments. And then we measured the actual state execution time. And we see here on the x-axis of this diagram the number of variables transferred. And I said we aimed at 100,000 variables, so we see that point here. And also our aim was to do the state transfer in less than 90 milliseconds. So this line here gives you the threshold of 90 milliseconds. And we see here with our OPC-UA transfer, in the worst case, we had in our experiments a transfer time of 42 milliseconds. So in this case, the state transfer was successful, and we could update the control logic without interrupting the production process, without losing a single execution cycle. We also did measurements for even larger number of variables, but these are more theoretical because we don't see these situations in practice. But in general, I think the approach scales quite well. We also implemented a fast variant of the state transfer based on inter-process communication. This then only works on a single node, but for some update scenarios that's also valid. Because you don't have to do the network transfer, then this is much faster, and here the worst case execution time was 17 milliseconds. Good, and we also measured then a little bit where is the transfer times spent, and found out that most of the time is spent here in reading the memory and writing the memory. So the serialization and deserialization took the most time, while the overhead for the networking was really minor. To improve the external validity of the results, we measured also on different hardware platforms. So we used a single board computer based on a Raspberry Pi. We measured on a server PC, really simulating a bigger cluster of computers, and then on an industry PC running a Xeon E3 processor. And we see here the different curves which we arrived, but all of these devices, they were within our requirements, and the state transfer was really fast. Good, this was an approach for updating systems at runtime using cloud-native technologies and utilizing container orchestration frameworks. We are still exploring what are the practical limits of transferring the internal state in multiple chunks. So far, we only have a single chunk of transferring the internal state, but there could be more sophisticated approaches that could make the approach then even more flexible to run with shorter cycle times. But then we're also looking in general on how we can transfer cloud-native technologies into the industrial domain. For example, we have real-time requirements, we have very high reliability requirements and high security requirements, and we need to check all of those requirements, whether they are fulfilled if we use these container orchestration engines and container runtimes. And then also we have resource-constrained devices, embedded devices, and there's still an open question how far we can go with those cloud-native technologies. So there you have it. I summarized the 3 different directions for research at software architecture research at ABB in process automation. We had the rule-based code generation as an example for model-driven development, where we generated source code based on the topologies specified from chemical engineers. But still we have here a lot of open questions. So what are appropriate abstraction levels for the topology models? How to use these generation approaches for other kinds of control logic besides interlocking logic? And then also how to use the rule-based generation for other kinds of things like process graphics generation, simulation generation, or even other things. We thought a continuous deployment through a plug-and-produce field device commissioning approach, where we had a plug-and-produce service that automatically discovered and configured devices in a network Here we are still exploring, can we synthesize more device parameters, how to lift this approach from individual devices to actually production modules, and then maybe also use such an approach to simulate device behavior and use that for testing control logic before actually commissioning those devices. And finally, we saw the cloud-native infrastructures, where we had an approach for Bumpless updates using container orchestration, where we utilized the container orchestration engine with Kubernetes and implemented a custom Kubernetes operator to conduct a state transfer between two PLC programs. Here, the open questions are regarding the practical limits of transferring the internal state in multiple chunks, and then also to find out how far we can use cloud-native technologies in the industrial automation domains, giving all these regulative requirements, real-time requirements, safety requirements, and so the limits are still unclear. These were 3 topics, but we have a lot of more topics in software architecture, software engineering, in process automation at ABB. So I encourage you to check the publications that are behind the research I just presented, and also check for other publications on the different topics that we have here, so you can learn more about the research that we are conducting at ABB. And finally, we also have open positions in research at ABB for research scientists for software engineering and for system and software architecture, and also always open to work with interns and master students on these topics that I just presented. If you're interested in that, just go to abb.com/jobs, and then you can look for research jobs there. So thank you very much for your attention, and have a nice day.